Okay, welcome to another BIMSA member seminar. It's a pleasure to have Professor Jie Wu. He's the professor in topology group at BIMSA, and he's going to talk about topology of complex systems.
Okay, so thank you. Thanks, Don, for asking me to give a talk in this important seminar. Right? The talk basically aimed to the general audience. And if anybody interested in anything in concrete topics, we can discuss later, particularly for junior people. Right? We are happy to try to see more people to involve or at least the project or our ideas what to do. So well, as a title, we try to say about something about topology of complex systems, right? So here I start with the first one. So I try to say something like kind of start with a dream, right? Maybe by means of dream is not realized at the moment. Okay, so we hope as a BIMSA, because we are aiming to apply it in the sense supported by mathematics. So I hope in future, at least, well, let's make timing within my life. Okay, I hope to say something good. Means there are certain things that technology can be developed in the sense that this is really get high, say, impact on science and technology, and maybe we require more. There are some new mathematics can try develop, which can impact the future of the mathematics, right? That's, I guess, the things that we try to do such things. And of course, as a team, I don't say too general. This is should be effort for all members try to reach such a goal. And I just share experience during the last few years. We try to move such a direction. Okay, so here's the things we try to do now. So we say I'm in charge of the algebraic topology and its applications, right? And I said try to make such a dream. So first thing we need some kind of like a goal or fundamental goal, right? And the fundamental goal is supposed to be not so easy to reach in a short period of time, right? Say, for instance, in knot theory, actually people never really give a complete classification of knot, but they keep working on that. Well, in algebraic topology, people never able to classify finite complex up to homology, right? And homology group, of course, we cannot finish, but we are working hard on that. So the choice, we need to choose something beyond the mathematics. That means you have to aim to science. So the choice of what I proposed is so-called scientific challenge will be tried to give a proper understanding, or you need a scientific or mathematical understanding on higher order interaction complex system, right? And such a challenge, it definitely should be defined. It's not a simple question. So you can see that people struggling for a long time in physics about n-body problem, right? We may not be even well understood for three-body problem. But now the proposed question even harder, right? So secondly, we have to recognize that such a kind of a high-order interaction actually popularly exists in the sciences, right? So once you move from physics to biology, try to understand what is life. Well, high-order interaction immediately comes out. And then, of course, question back to us, how to understand, right? Okay, and another thing, we'll see that so far, actually, the mathematical tools are limited to understand high-order interactions, right? So in other words, there are no well-established theory how to properly describe, even describe. So that's the background things. Now, what we should do? We should try to develop something which can understand, make some progress to understand that, right? So from my point of view, certainly we try to understand something, some topological series can try to approach such a direction, okay? Okay, so now what's next? So I move to next. So what topology can do? If you say set up such a question, well, this is exactly in the principle of Binzer, we should search for such a, such a research through the interdisciplinary cooperations, because we want to aim to something beyond mathematics. So we don't want to sit down and make any models what we believe is correct, but in terms of practice, maybe not correct, right? So it will be good to cooperate with people really who understand the practical problems. And we try to introduce some topology series to those models people try to develop, say, from statistics, physics, or any other ways, okay? So we try to make such an effort in that. Okay, so now let's see. What's the next? Okay, so now I'm trying to aiming to so-called higher order interaction complex systems. So we have to watch around how people to set up these mathematical models to that. Well, there's something I call straightforward extension of graph models. Well, once your graph theory, you can try to understand pairwise interactions. So in any object, I can draw a graph. Okay, if there's a interaction, let's draw a line. Okay, that. And now there's a way you can say I can go beyond a pairwise. Let's say if you three of them come together, okay, let's think about this is a triangle. Okay, now you get the 4, 5. Okay, so this is so-called simplicial complex approach. Actually, a lot of people was doing in such a way. Okay, and now I make a little bit mathematical definition, right? So what is a simplicial complex? Well, here's an easy way, abstract definition, right? By means of abstract simplicial complex, just a collection of finite set. Now, there's a little bit of rule in here. So it's supposed to be closed under subset operations. In other words, if you choose A, B, C, you just imagine as a triangle, then the face AB, BC, AC is automatically selected, right? This is actually how the abstract simplicial complex is defined. Okay, so now, once you have abstract simplicial complex, well, traditionally, or even more than 100 years ago, people already know that we have a geometric shape comes out. There's a one-to-one correspondence between abstract simplicial complex and real geometric simplicial complex. Okay, more specifically, if you think about abstract simplicial complex up to isomorphisms, if you think about polyhedrons up to pairwise linear isomorphisms, okay, they are actually they are isomorphic. Okay, so this means that once you get any data, you try to use simplicial complex as a model, or geometry automatically comes in. Okay, then of course you can say I can use topology, just compute homology, pretty number. Of course, you can also think about I can put in geometry. If you think about in algebra, you through such a way, this will be fine. Okay, so this will be a change. Once people try to use simplicial complex model for any higher order interaction, like a complex system as a model, math model, then all mathematics can go through such a way. Okay. Now let me say, yeah. Well, okay, say a little bit. Okay. So here's a typical example, a so-called like a chat nerve complex. Actually, this is people in applied call clustering, right? So we give a set, it's just a collection of subsets, and the union will be recover that. Now, in terms of topology, you get topological space, you can say a cover, open cover on that, right? And if you satisfy a little bit of condition, there is a beautiful classical chat nerve theorem tells that if any finite intersection is contractible, and then yes, they are missing something. Yeah, it should be any finite intersection is contractible. Then what you get, simplicial complex, you will get the homology equivalent to the original space. So that's a beautiful. Okay, so pay attention. I think there's hypothesis condition here. Okay, it's not true for anything. Okay. And this is exactly the foundation for current topological data analysis. Okay, and of course, people can use a simplified version, so-called vectorial Lipschitz complex. You instead of look at the intersection of say 3 of them, let's look at the pairwise intersection. That's easier to compute. And instead of looking at one homology, let's make multi-scale. So you make filtration on that, and then you get a barcodes and used in data analysis. It's quite successful and quite popular now. And another way, if you take a graph, actually people is used a lot, so-called like clique complex. Okay, you look at the lows, which you get like a fully complete subgraph, and let's collect it. Okay, so this is I call the simplicial complex approach. Okay, now there's a bit of question because we are trying to go a bit something beyond the current approach. So the first one, actually, people in applied will be say, well, there are some limitations of the simplicial complex. They are not even happy for this little bit constrained condition. So, say for instance, a simple example, people use like a co-authorship network. Well, you may not all phase will be inside there, right? If in biology, you can find a lot of say, such models. In social network, a lot of models. So now there's a fundamental question. So if I give a general one, let's call, say, hypergraph, okay? Now the question back to topology, can you still extend, say, simplicial homology theory to hypergraphs? Well, the answer actually is yes. So this is what we have done. Let's like, this is exactly coming from what we call the Professor Yaw's GLMY theory. Okay, so you can use this theory. We can extend homology theory as general as possible so that we can apply to more general objects. Okay, so now let's see. So this is, I just say, because of timing, I don't want to say more details. So briefly speaking, of course, you just, if you, what happens if you like constraint condition in simplicial complex fields? That means that you are difficult to define the chain complex. So chain complex, you have to use phases to do that, right? So you have to do alternating sum as a boundary operator. So that's a problem. Now, brief idea, because of time, I don't want to say that, is as follows. You think about a hypergraph, always you get missing phase from topological view. So missing phases are just collecting back. Of course, that's beyond the hypergraph. Let's go as a chain complex, consider chain complex as algebra representations on the geometric object. Then you can, in the category of chain complex, you can move it down so that you can take the smallest the chain complex covers that, right? This comes from like calculus, like influence, supplement, what we discussed. And turns out all this in the level of chain complex, the influence, the supplement, actually they are induces isomorphism in homology. So this is given natural extension. And that's exactly the way we are doing. Developed from Professor Yaw's GLMY homology. Okay. Now, there will be, I say a bit,
Can I ask you a question?
Yeah.
Why is the co-authorship not successful to be modeled with simplicial chain complex?
Say it again.
Why is the co-authorship network cannot be?
Co-authorship. Say, for example, I try to detect the ABC, like co-authors. So I mean, it looks like a triangle, but the ABC has a co-authored paper, but AB may not have.
That's right. But then if you define co-authorship you should just decorate the graph, right? So at each vertex, we can say the most immediate adjacent vertex is a co-author, and if not, it's not a co-author. So if you have a rectangle and A and B are co-authors and C and D are co-authors of A and B, B cannot be a co-author of C because the distance between B and C is 2.
You can use the distance,
Yeah, you can add a decoration.
Well, let's use like models. The co-author, I would say, just immediate. If you try to aim a simple complex, let's take example, right? Okay. Of course, in practice, for some hypergraph, you can treat it in a different way. Say for example, we actually not practice to testing co-author. We look at like in the case of drug design, you get some chemical element from the proteins and the ligands. Definitely, if they have an interaction, they must mixture together, right? Okay. So in that case, now theoretically, with this move to mathematics, you should extend the tools as general as possible. Okay, so now the next one. So it will be actually there's one constraint condition is that for simple complex, if you know the vertices, the simplex must be uniquely determined, right? So I get 3 points actually is the converse count of the 3 vertices. So if I get the 3 vertices, can I make a 2 of the like a multi-simplex? And such a notion, say for example, if I get 2 vertices, I can get a line, right? I can get 2, make a circle. And such extension actually exists in algebraic topology, which is so-called a data set. And it is appeared in the standard textbook of algebraic topology, so-called data complex. And so, such a way, such a model, so you get a little bit of extension, and it can be used in applied, say, neuroscience or somewhere. You not like really like cutting the cakes like simplex. And this has some advantage is that you can make simplicial complex instead of look at the vertices. I would say make a multi-layer or graded version. I make say vertices on the 0th floor, 1 simplex on the 1st floor, and then now each simplex is used as a symbol. And then I use the faces as arrows. So this will be like a way, if you look at it, something like a quite like a feed-forward network description, right? And they do have a geometric realization. Everything goes same as the simple complex. Okay, and okay, so now this is one. Okay, so if anybody make model such a way, there's no problem for we can still use all topology theory to apply to that. Now the next one will be actually related to this talk I was mentioning. You use these ideas of there. So if I get a simplicial complex, let's assume like some faces are missing. Okay, show you some model. Now, if I use a data set, let's assume like some faces are missing. So you go something beyond that. It turns out that if you take simplicial homology, can be also extended along the same ideas. Actually, this is an amazing idea Professor Yao proposed for the past homology or digrahs. Okay, we can use this developed there, and it works here. In the end, I will mention that this can be applied to Longlin Wu's hypernetwork models. Okay, so now what's next? Well, the first one to the next one, I back to Longlin's model. So instead of the locate, they use 3 vertices as a high order interaction. Let's consider some models use high order interaction, will only give a lot of talk, right? As a driver of the digraph. So the model you still looks like a digraph, but this high order interaction will be moving around. Okay, so that will be give another interesting. So you have okay, so give you still have a still digraph, but they may change. Okay, so now the first question, the backwards to mathematics was the first question. Okay, so develop the say algebraic topology of digraph first. Once they move, okay, technically we just move it. Okay, so if you weight it, we can weight it. Okay, so fundamental part is just give you as simple as possible, just a digraph. Now let's try to develop algebraic topology out of that, right? This is the actually is one of the main projects in our team try to use like what's so-called develop a GLMY theory on these directions. And now as I mentioned, in algebraic topology of this direction, we can say one is develop homology series on digraph. Okay, so give some tools, as many as possible, mathematical tools. So in case people want to do analysis on this network, you can try to use it. Secondly, well, we can try to look at what's going on for homology theory, right? So basically, algebraic topology of two parts. Now, well, say actually it will be fun and actually found something is quite challenging mathematics comes out if you try to work on homology theory out of that. Okay, so here's the existing information. So actually, we listed some information, right? If you look at the graphs, you try to develop the algebraic topology, it's not really fully new. So historically, people even backwards to, forgot, 60s or 70s or even earlier, 50s, so you try to develop a lot of tools, right? There's an area called topological combinatorics, right? So there's well, this table tries to do a little bit of classification and give some indications how you can develop algebraic topology. Say, for example, if you take graphs, you look at the clique complex, right? Look at the clique complex. For simple graph, you will get a simple complex. But if you can look at it a bit further, if you change, just simply change it as a multi-graph, right? Well, you will not get a simple complex. And the data set is the proper notion of that. And now, if you look at like a path complex, right? Exactly look at the pathways. That's the path homology Professor Yao was introduced. If you look path complex, it will become to be hypergraph because the point is like if you look at A to B to C, okay, so this is the path you choose. Now you look at the phase. If I delete C, well, A to B, it's there, it's okay. Now if I delete A, B, C is there, but if I delete the middle one, that will be a problem. You may or may not have an arrow from A to C. So in other words, you will not get the simple complex. So let's the object to go out, right? Now the description can be use hypergraph. But then now you try to extend to further. This construction go to say quivers. Okay. Now in this case, yes.
Yeah. So actually curious. So in this path homology, is the distance between 2 points infimum of all possible paths, or is it, how is it defined?
Oh, I will review a little bit. Okay, I will say that shortly review. Okay. So let me explain. I will back to answer your question. Okay. So if you go to say multi-graph or quivers of this construction, then actually you will come out to the notion of our notion so-called super hypergraph. What do we call that? Right? You extend. Okay. So now. Now, here's before I review a little bit path homology. This is Professor Yao introduced like more than 10 years ago now. And there's a background motivation. It's actually people in physics were actually always struggling how to describe these calculus, right? So this is some motivation is even earlier in physics. They always try to develop a theory. But as usual, physicists they can propose us very smart ideas usually have no good theories to support. They give some examples. And the paper, Professor Yao's paper, is got a long paper to establish these ideas, right? So past homology, first the motivation is like you try to get the discrete differential calculus. Okay, that's the background. Now, secondly, I try to say this briefly. I say, okay. So this is actually an extension of the in category theory. You know, any category you get the nerve complex, right? So think about digraph is a kind of a category, but no composition operation. So construction of past complex is like a nerves complex, right? If a transitive digraph, you will get the nerve exactly. So this notion actually is quite strongly connected to the categories, and also there's some other, as I said, physical reasons and some for even algebraically to that. So it's a very smart idea how to develop this theory. Okay, now because of well, still have time, right? How many minutes I still left?
You have time.
Okay.
You're not 25 minutes.
Okay. Okay. So now, now I just explain a little bit. So this is 10 years ago. Like now we call GLMY homology, or originally called past homology. Then, as I said, actually, in terms of applications, you may try to develop as many as mathematical tools, right? In case people may have a different purpose to apply to that. So there's many other homology theory actually is also good to develop. Just and another thing, well, as a connections with mathematics, you can always think about that. It's quite good. It's kind of like what ideas, generalized idea of nerve complex. So it's a natural topology construction for digraph, and the homology theory is also under development. Okay, so now I just say a bit on homology theory, okay, because timing, so I just say a bit. So how homology can be defined? First of all, how can you define homology on digraph, right? Well, by defined homology means in geometry will be like a continuous deformation, right? So if I'm mapping from one space to another mapping from one space to another, I can make a cylinder, right? Make a parameter from 0 to 1. If such a mapping from top to bottom can extend to a cylinder, that means homology. Okay. Now, such a construction you can try to extend to digraph. So if you have two digraph maps, okay, you just say send arrow to arrows, vertex, and you try to construct the cylinder in digraphs in a canonical way, right? In terms of a good graph theoretical description. Now, what's that? That is actually so-called box product. So I have a digraph on the zeros floor, and then on the first floor, from 0 to 1, I have arrows move up. Right? That's it. That's a cylinder. So it's intuitively realistic. Now you think about the extension of such a map. So what's that? Well, you look at the image. The bottom one is under CF, is a certain subgraph. Top one is under G, is certain subgraph. But those arrows, you have to send to be some arrows. So that means that you have to be uniformly, right? Move the image of the F to G. So this is that's how I say, like floor of this one. And such a floor, under digraph situation, you get positive, right? Well, you can repeat it. Then you get iterated. So there's something mathematically you will see that you can look at the floor, or even I would say later say even try to develop an index theory or anything to try to go. And now of course the homology you can define because you want to make an equivalent relation. You can say we're invertible, right? But if you don't want to consider equivalent relation, you just keep going of that direction. That will become the floor. Okay, so now let's see a bit, right? Okay, so now there's some along this direction. Actually, this is 10 years ago already. This notion introduced by Professor Yao 10 years ago, and there are some, they try to work out some fundamental theorems, right? So Poincaré's lemmas works, fundamental group is okay, and Poincaré lemma works, right? Horowitz theorem is not clear. You can introduce a higher homotopy group. Okay, so now because this move a little more technical, so I'll just say briefly. And the homotopy group, you try to describe something like what homotopy group in space. You get a sphere, you get a mapping, right? You try to up to deformation. Now, in terms of a digraph, well, you look at the shapes of that. Okay, we can take a cubicle or there's grapes. Okay, let's try to map into there. If I map boundary to a point, this will be like holes there. And you can try to define a homotopy group in such a way. Okay, and some progress. Well, this is a Horowitz theorem, as I said, we have not worked out yet, but this is the corresponding to geometric way. So we have something through homotopy to homology. Okay, and they supported each other, right? So that's the information and some little bit of progress so far. We only get like a pub sequence that works, no problem. Why is the pub sequence is important? That pub sequence means that in algebra topology, so in algebra, if you get a homomorphism, two important things you'll look at. One called kernel, another one called co-kernel. Now you give a continuous map from X to space, X to Y. You have to think about what is the kernel in the sense of homotopy? What is the co-kernel in the sense of homotopy? Well, the kernel is so-called homotopy fiber. Co-kernel, so-called homotopy co-fiber, right? So co-kernel works well for long exact sequence homology theory, and the kernel is a long exact sequence for homotopy theory. So once you set up any homotopy theory in any category, you try to look at what's going on for where the pub sequence works. If it works, that means there's something, this mapping and the kernel, co-kernel, all these things. Okay, okay. So now let's say I move a bit the recent work. Okay, so this is exactly the recent work. It's Longling's work called HyperNetwork, right? And this paper already published, and we're happy to see in this PNAS paper. So there are some use HyperNetwork modeling, and then we can detect the topology of high-order interaction systems, right? And I will not say the detail, so we are happy people at least recognize. I will say a little bit. There are some mathematical foundations on that. Okay. Well, because of time, I will not explain in detail. In the end, I will say a little bit how can we make a modeling on that. Okay, so this is the so-called description for Longling's of HyperNetwork. Okay, so interaction supposed to be between different dimensions of hyperedges. Okay, so in other words, you have your arrow, you may act on this point. Conversely, you will be backward. So yeah, one can think about a lot of mathematical model to that. Okay, in the end, I will see a little bit. Actually, at least we give one, proposed one. And such a model sounds quite a success because people, we can extend GLMY homology in such a way and can really describe, give some description in terms of practical questions. Okay. Okay, now, of course, you can try to propose other ideas, okay? They just try to understand what is higher interactions in these models, okay? Okay, so now, I think I try to see a bit, okay, how we performed, okay, as we report. So let's previously we give some general idea, and then now let's say we try to do the following direction. First of all, we make some mathematical idea, and then we try to corroborate with people, to test it, to see whether it is good. So we do some applications. So this application, many of these applications should be corroborate with, say, Longling and the other people, try to testing whether this theory make sense or not in terms of application. So that's where to, and then we have some, there's an output already here, right? This works already last year, so we just use Professor Yaw's this GLMY homology, so we don't want to change anything in the definition, and we choose the select the proper questions in terms of that, and it turns out it was successful, right? And then we can choose more, right? And so this some works on here, and there's some more works, right? And related to these extensions of past homology. So now we extend some homology and then try to find the practical questions. And I just put a remark here. Actually, there's another Pinus paper we published. It's not really use algebraic topology. This is the first time we introduced the notion so-called not data analysis. So we just changed the classical knot theory in terms of mode scales. And it turns out the result performs much better than topological data analysis. Okay, so this will be others. And we also perform some mathematical research. So I just display a few. So in this direction also, we try to develop math theories, right? And I just display a few things here. Okay, so now I say a bit more on the what's going on for future. Maybe that people you are more interested to it, right? So far there's one thing we actually think about. From mathematicians always think about, right? If I take a usual homology, can we try to make a geometry? Can we make a bundle series to that? You can ask what's the shift series to there, right? Always mathematically, we always like whether it can make a twistings, right? So this we are moving in that direction. We try to see, right? We try to get something in group actions and move a bit slowly because we try to do some mathematics and we try to find the possible applications to design some project to see there's some useful in terms of application, right? And as I said, actually, once you just look at the definition of a homotopy, you actually, I think for many of you can open up many questions in mind, right? If I take flows, what's going on next? Now, of course, these things, as I said, we only go a little bit, just try to get the pop sequence works. But the homotopy, if you can think about it in many different ways, say index theory, right? And this question is still open. And so if you're interested, we can chat in more detail and how can we develop in some nice series on digrahs, right? Say, okay. Now okay, so now I say a little bit. I still have a bit of time, right? Now I can say a bit about how.
You're now 38 minutes. 4 minutes.
Okay. So now I can take 1 minute to describe that. Okay. So how can we describe like age? A, B is L, X on C. In terms of mathematics, we should use algebra. So if I think about from A to B is L, I just take a bracket, A to B, right? Okay, A, B, and that's it. Now what's going on? If I take A, B, then C. That means A, B, L first, then X on C, right? Okay, now let's say A, B, C, D. But each time I have to take a bracket. Exactly happens, right? If you search in algebra, now you opened up quite a famous in combinatorial group theory. Actually, I can quickly remember Magnus' book, right, published in 1960s. So Magnus tried to look at the commutators in combinatorial group theory. Actually, look at the algebra, you can do that. So Magnus called this the bracket arrangement, right? So if you take, say, something like for A, B, C, D, okay, now you have many choices. I think 5 possible brackets, you can make it. And if you arrange of 5 possible this bracket arrangement. Instead of looking at the commutator, you look at it like a non-associative multiplications. What's that? This is touch with, if you can extend the shape by, say, two-dimensional. This Starship's infinity game to do that. So in terms of mathematics, actually, there's a lot of mathematics behind that, right? So far, you can see that this operation can properly describe what learning want. Okay, and then in our purpose, because we want to develop some topology theory, so extend Professor Yaw's like past homology in such a way, and then you can then we got works well in terms of that. But mathematically, there will be a lot of things you can see what's next, right? Certain type, right? As I said, where there's a Lie type, say for example, Lie type high order interaction complex system, because I think about the Jacobi identity holds in certain strange way, right? So we do have a lot of things we can do. Okay, so now also there's another one where things is pushing like your filter, right? Okay, so as I said, we try to develop something connected to mathematics as well. We can open these ideas to discuss, right? Okay, now, yeah, I think another thing will be actually we just opened up. We actually, that's our paper, it's opened up, so-called not data analysis. Okay. And then there will be a lot of questions you can open up, what to do, how to apply not theory in AI and data analysis, right? Okay, so now I think there will be more should be. Yes, one is my belief, right? So this is belief, right? Good math should have a good applications. Well, whatever we believe, that's the same. Okay, that's my philosophy. Okay, so we should end of my talk here. Okay, okay, thank you.
Okay, questions? I have a question for you. So when you set these with these digraphs, for instance, you cannot do usual way homotopy theory unless you look at hypergraph constructions, right?
Well,
but let me ask you my question first.
Yeah.
So let's say I have a digraph. I have vertices and edges and multi-edges.
Yeah.
Why can I not think of the set of vertices as the zero level data associated to the graph? Then the set of one vertices as the T1 of that set, like first tangent functor applied to the set gives you all the one simplices. Second tangent functor gives you all the double arrows. Third tangent functor gives you all the triple arrows. By injection, all of these are injected inside each other, and then I get something like double complexes you get in a spectral sequences to calculate homology. Why can I not do that?
Well, maybe it's not means why you cannot do that, right? Actually, this is the question what we were saying. So you want to try to look at the tangent. Let's do simple case. Let's don't look at the multi one as simple as possible, just diagram, right? And then that's a
but for me, tangent is not really the tangent in differential calculus. Tangent means just one simplices between vertices. T2 means two arrows between
that.
T3
right?
means three, and then this gives you a ladder.
Well, a lot of ways
a
lot of ways. One way is so-called magnet homology, which is try to counting steps of that, and there's some homology theory related to that. Again, it will work a lot, and there's some interesting connections between magnet homology and path homology. And when you say tangent, I think Professor Yao proposed a question. Still, we have not solved it yet. So you think about this digraph. What is tangent digraph is? Because we can try to ask the geometry. Okay. So what is the tangent? Say line bundle looks like. That's some question we have to look. Of course, you can think about that with one step, two step. Yeah, some people also think about some view. Maybe you get different.
Okay. We can discuss. More questions? If any.
Can you be more explicit about the physics model Which is starting point?
Oh, the physics model is like you backwards to this motivation. I refer to you think about like this beginning, right? Here it is, right? Your physics. Physics try to think about what you get like this the harmful chains the forms in a way, and now that's in the continuous situation. Now the physical motivation is trying how to discretize, right? So if you look at the cohomology, instead of cohomology, the functions on that. So you on functions on paths like you are exterior powers on that. So that's why you can extend to that. Now you move to homology, of course, you just look at the paths. Yeah.
More questions?
I'm actually not a mathematician. I was a speaker for a digital economy seminar, but I think the idea you developed possibly could have a wide implication beyond the topology and mathematics. I'm actually intrigued at the graph. You said the first tier, second tier, and third tier, and making the network more complex. I have two questions as someday outside of your subject area. First, I think the first tier graph might contain more fundamental information. So is there any way to statistically extract the first tier graph that's fundamentally underneath? I could possibly consider as the basic structure of the network. And the second, are there any conditions or assumptions that would make this first tier graph unique? Because you say if you, you give a really simple and yet like intuitive example, like A, B, C. If I delete C, then A, B is still. If I delete A, then B, C is still, but I miss A and C. But sometimes, like the co-author network and the network we have, and, A, maybe the C got or B got through, and then if I'm missing B, and A and the C could still match and produce a paper just because, they already connected in a way. Yeah. So I was thinking about it in this way. Then if I want to extract this fundamental graph, then it could be two ABC or ACB or, ABC. And then there's no unique representation of the first tier. So that's just what I think.
Okay. Yeah. Actually, there's some once in practice, I would say refer more back to this. Let's go back to statistic models, like the longest one. Okay. So you have a graph. Certainly, you can see hypergraph. That's with the extent, and then you can only will call like a first order hypergraph, second order hypergraph. Actually, you can make more and more complex in terms of levels of that, right? So that's of course you can see there's potential. It depends on your model. Now, what I say is that once you get a clear map model, say can determine that, then our question will be, okay, so we can try to develop a topology theory to working on that, your model. Well, model means at least in terms of mathematics, right? So we can propose a new idea. That's why we say cooperate with, say, from applied side. So we can first we need to work out a certain model. Now each model, then we can do mathematics. So the advantage from Vincent would be like this. So people, if you purely work by applied people, you have to search references to find the mathematical tools. Now, if you put your question into BISA, we can try to create some. Once your model is clear, defined properly, we can develop a series without any. Well, we can try to write the first paper, right? So that's a difference.
More questions? Okay, let's thank Jiawu again.
Okay, yeah, thank you.